Welcome to a lesson on one-to-one transformations. A transformation T from our n to our m is one-to-one if, for every vector b in our m, the equation T of x equals b has at most one solution x in our n. Or more simply, for every output vector in our m, there is at most one input vector in our n. Another word for one-to-one is injective. And here are some additional equivalent ways of stating T is one-to-one. For every vector b in our m, the equation T of x equals b has 0 or 1 solution x in our n, while having 0 or 1 solution is the same as having at most one solution. And different inputs of T have different outputs. If T of u equals T of v, then u equals v. Below we have a mapping of a one-to-one transformation. Notice different inputs in our n have different outputs in our m. Or we can say, for every vector b in our m, the equation in the form of T of x equals b has 0 or 1 solution, or at most one solution, as stated above. Now I do want to mention something here about where you can have 0 or 1 solution in our m for every output vector b in our m. There could be, for example, some other vector, let's say vector b sub 4 in our m, where there is no corresponding input vector for vector b sub 4, and this would still be a one-to-one transformation, again because it does satisfy the definitions above. And now let's talk about equivalent ways of saying that T is not one-to-one. T is not one-to-one if there exists some vector b in our m such that the equation T of x equals b has more than one solution x in our n. So looking at the mapping below, notice for vector b sub 1, there are two corresponding inputs or two solutions to the equations in the form of T of x or T of y equals b, and therefore this is not a one-to-one transformation. We can also say T is not one-to-one because there are different inputs of T with the same output. Notice the inputs of the vectors x and y give us the same output vector of the vector b sub 1. And also the transformation is not one-to-one if there exist vectors u and v such that u and v are not equal, but T of u equals T of v, which in our case, notice vectors x and y are different vectors, but T of x does equal T of y, which is why this is not a one-to-one transformation. And now this theorem relates previous topics to one-to-one transformations. Let A be an m by n matrix, and let T of x equal ax be the associated matrix transformation. Then the following statements are equivalent. T is one-to-one. For every b in our m, the equation T of x equals b has at most one solution. For every b in our m, the equation ax equals b has a unique solution or is inconsistent. This is the same as saying there's one or no solution. Ax equals 0 has only the trivial solution. The columns of matrix A are linearly independent. Matrix A has a pivot in every column. The range of T has dimension n. And if you've learned about kernel, T is one-to-one if and only if the kernel of T contains only the 0 vector. So again, all of these statements are equivalent, which means we can use statements 2 through 8 to show a transformation is one-to-one. But in practice, we often use number 6, where to determine if a matrix transformation is one-to-one, we write the transformation matrix, or matrix A, in either row echelon form or reduced row echelon form, and then determine whether matrix A has a pivot in every column. If the answer is yes, the transformation is one-to-one. If the answer is no, the transformation is not one-to-one. So for an example, let's take a look at this first matrix A. The first step would be to write the matrix in either row echelon form or reduced row echelon form, and then determine whether there are pivots in every column. Notice for the first matrix A, we have a pivot in column 1 and column 2. Because there's a pivot in every column, the corresponding transformation is one-to-one. Looking at the second matrix A, we have a pivot in column 1 and column 2, but not column 3. Because there's no pivot in column 3, the corresponding transformation is not one-to-one. Let's take a look at a demonstration of these two matrix transformations. This first matrix transformation corresponds to the first matrix A, shown here in the upper left-hand corner, which we classified as one-to-one. where vector x is the input vector, or the vector in the domain, and vector b on the right is the output vector, or the image of vector x, under the transformation T. As we drag the input vector, notice how we always get a different output vector, which verifies we have a one-to-one linear transformation or matrix transformation. For the second demonstration, we're using the second matrix A, which is shown here in the upper left-hand corner. You may recognize this as the transformation that projects vectors onto the xy plane. And what we'll notice here is for all the vectors that terminate on this purple line, the output vector is the same. So the output vector of B has more than one corresponding input vector, and therefore this is not a one-to-one matrix transformation or one-to-one linear transformation. If I change the output vector to a different vector B, and the vector that terminates on this purple line gives us a vector that gives us the same output vector, again verifying this is not a one-to-one matrix transformation. And just to show one of the other properties, if I change B to the 0 vector, notice how again the equation Ax equals 0 has more than the trivial solution. All these vectors x are solutions to the equation Ax equals 0, again showing this is not a one-to-one matrix transformation. I hope you found this helpful.